Hey, we can start now. Let me check one more thing. Okay. So welcome to this P&S course. It is called Designing and Evaluating Memory Systems and Modern Software Workloads with Ramulator. So this is the first meeting, and in this first meeting, we will discuss the course logistics, and I'll also do a quick introduction to memory systems and how we simulate memory systems using a simulator that was developed in our group, and that simulator is called Ramulator. And RAM stands for Random Access Memory, as you may already know. So like this is like where the name is coming from. Okay, so here's the course content. In this course, you will learn in detail how modern memory systems operate. So here, when I say memory systems, I mean the memory controllers and like the actual memories that the memory controller is like managing, right? You'll also design new DRAM and memory controller mechanisms for improving overall system performance, energy consumption, and reliability. Not all at the same time necessarily, but yeah, why not? You will simulate and understand the memory system behavior of modern workloads such as machine learning, graph analytics, genome analysis, and more. Okay. So here are the key takeaways. So this is this P&S course is aimed at improving your knowledge in computer architecture and memory systems in general. So like we really expect that you learn a lot from this and like you like gain some like low-level experience and understand like how these like low-level memory controller and like DRAM mechanisms work. You gain technical skills in simulating memory systems. So yeah, you get used to like how to use simulators, architectural simulators by using Ramulator, I guess, as a use case. And you develop critical thinking and analysis and interact with nice group of researchers, familiarity with key research directions, technical presentations of your project. So this presentation of your project is the last step of this course. So like after you select a project to work on, you like accomplish the tasks in that project, we expect you to present your work to our research group that I will introduce in a minute, and also to like the other students taking this course. Okay, so the key goal of this course is to learn how state-of-the-art memory controllers operate, design new DRAM and memory controller mechanisms, and evaluate your mechanisms using simulation. Okay, so here are some prerequisites. Digital design and computer architecture are equivalent course. So I assume like you have already taken a similar course or you have sufficient knowledge in this area. A good knowledge in C and C++ programming languages. I guess especially like C++. Anyway, so like interest in making things efficient and solving problems. And the last item, interest in understanding software development and hardware design and their interaction. Okay. So the main lecturer of this course is Professor Onur Mutlu, and here's some information about him. So he's a full professor at Information Technology and Electrical Engineering Department at ETH Zurich. This is he's at ETH since September 2015, and previously he was a professor at Carnegie Mellon University, and he worked at various companies. You can see them listed here. The best way to reach him, if you need, is his Gmail address, and yeah, you can just email him. He's doing research and teaching in a lot of different areas, mostly related to computer architecture, but he's also like doing research in bioinformatics. And yeah, you can see the list here. Okay, so a little bit more information about who we are. So this is me here. My name is Hassan, and I am the lead supervisor of this course, but we have 4 more supervisors, and you can see them here. So basically how this course is gonna work is after you, so we'll provide you a list of like projects available, right? And then you will like tell us your preferences, like on which projects you would like to work on. And after that point, we will assign you mentors. and you will work closely with your mentors to do that project, basically. Okay, and if you want to learn more about our research group, you can visit our website. So here's a photo from April 2020. And here you can see our almost entire group. And yeah, our motto is think big, aim high. And again, you can visit the website for more. Here's another list of research areas of our group. So in general, we do work in computer architecture, hardware, software, co-design, and bioinformatics. But here's a more specific list of areas that we work on. So some things that I will mention is that we work on memory and storage technologies, specifically focusing on DRAM, flash memory, and other emerging technologies, other emerging memory technologies. Yeah. So we would like to also know a bit about you. And for that, we have released Homework 0. It is a very simple form. So we just ask you a few questions, and we would be happy if you fill out that form and submit it as instructed in the form. You will basically upload it to Moodle. Yeah, and I think this is required. So you should really do this, because if you don't submit this, you cannot choose a project to work on, and as a consequence, that will make you fail, of course. Yeah, so please submit this on time. The deadline is, I believe, Wednesday next week. I'm not 100% sure. Yeah, but the deadline is on the website. Okay. So here are the course requirements and expectations. We require that you attend all the meetings. There won't be too many meetings. I mean, not meetings like this one. We will maybe have one more or two, but afterwards, once you start working on your project, you will be mostly meeting with your mentors when you need to meet them and ask questions. We expect you to study the learning materials. I already sent you a list in the email that I sent you 2 days ago. And yeah, so there are also more material on the website. So please take a look at them and and learn those. Each of you will do a project individually. So yeah, we expect you to work with your mentors closely and do a good job of it. Yeah, and we also expect you to participate, you ask questions, you contribute with thoughts, ideas, and read relevant papers. So although we will give you some description of the project, this doesn't have to be limited to what we describe in that project. So if you find better ideas, if you find ideas to extend the work, to add some new things, that is a nice thing that you can contribute. And yeah, so we will help you in all projects. And yeah, we really expect you to learn while working on this project. Yeah, and if your work is really good at the end, it may even get published. Okay, so here's the course website. And there you can find useful information about the course. So you will find Homework 0 there. You will also find a list of the mentors there. I will upload these slides to the website. And also please check your email frequently for announcements, as the one I made for the first meeting. Okay, so here are the learning materials. These are also on the website. So yeah, please make sure you read those at least until the second meeting, which we will schedule later today. Okay, yeah, so, and this is a slide about meeting 2. So in the meeting 2, we will announce the projects that you will be working on, or you will choose from. And then, yeah, so each of you will be working on a single project, and you will be having one-on-one meetings with with the mentors that will be assigned to that project. So we will also help you with the we will also help you with selecting a project that will be appropriate for your interests, skills, and background. Yeah, so I already mentioned that you should really study the learning materials. Yeah, so please do that. And afterwards, after the second meeting, there will be individual meetings with your mentors, so you can schedule those as needed. We may also do some additional meetings where we will do tutorials on Ramulator or like other related tools, and also give some like short talks about specifically about works that use Ramulator to design and evaluate memory controller and DRAM ideas. And finally, at the end of the semester, we will meet to listen to your presentations. Okay, so this was the first part about the logistics of the course. So if you have any questions related to this part, you can maybe ask now. And afterwards, we will continue with the second part. Okay, yeah, no questions, I guess. So in the second part, I will do an introduction to simulating memory systems using Ramulator. So here's some motivation for like developing Ramulator in the first place. So it was first developed in, okay, I think I don't remember the exact date, 2010 maybe, or maybe before that, maybe 2008. So DRAM and memory control landscape is changing. So as you can see in this table, there are various DRAM standards designed for different segments. For example, commodity systems use DRAM standards called DDR3, DDR4, and now DDR5 is also like starting being available. There are also DRAM or memory standards designed for other domains. So for example, for mobile system, there are the LPDDR segment, for graphics, the GDDR segment. And there are a lot of academic proposals as well. Well, I think I skipped another important segment here, which is the 3D stacked memories. These are also like pretty relevant today. We see especially like HBM2, like some high-end GPUs use HBM2 memories. Yeah, but there are also a lot of academic proposals. And basically, yeah, evaluating all these new upcoming standards, all these like academic proposals is challenging. And we need a fast and easy to extend simulator to be able to evaluate those things efficiently. Okay, so yeah, to this end, we develop Ramulator, which is a fast and extensible DRAM simulator. So yeah, maybe this title is a bit misleading. It's not only a DRAM simulator because it also implements a lot of memory controller functionality. So it implements, yeah, maybe we can discuss those later, but I will give one example. It implements different scheduling policies. So what I mean by a scheduling policy is the CPU or like multiple cores in a CPU system may issue more than one DRAM request, right, at the same time. And those requests are stored in a structure called a memory queue. And from the memory queue, the memory controller fetches these requests and serves them. But basically that policy of like which request to service first from the available ones in the request queue is important because like based on like how you in which order you service those requests, the memory controller or the DRAM subsystem, the memory subsystem achieves different performance. It affects the energy consumption, the power consumption of the system, and etc. Okay, yeah. So Ramulator provides out-of-the-box support for many DRAM standards. So here are some of them listed. it models the timing of non-volatile memories as well. So PCM and STT-MRAM, we can say those are the like emerging non-volatile memory technologies, although some of them are potentially used in existing products. So Ramulator supports multiple scheduling and row buffer management policies. So yeah, so I tried to explain like what is a memory scheduling policy and why there can be like different policies, but we will look into that in more detail. It is modular and extensible to different standards. So unless like the standard is like completely different and it basically diverts a lot from previous standards, which is not the case usually when you like, let's say, move from DDR4 to DDR5. The changes from like the functionality perspective are mostly similar, at least. Okay, so Ramulator can be paired with other simulators. We already have Ramulator integrated to a full system simulator called Gen5. And Ramulator is also integrated to a DRAM power simulator called DRAM power. Ramulator is written in C++. It uses the C++11 features. And at the time when the paper was published, it was 2.5x faster than the fastest open source simulator. And here's the table that is comparing different simulators. And it compares their execution time. Well, yeah, the second column, runtime, shows like how long the simulation takes. This cycles is showing like the cycles of like the number of processor cycles or memory controller cycles it took for the applications for the like workloads that are simulated to complete. So basically, when we look here, we expect these values to be very close to each other, right? So if you are simulating the same workload, that same workload, if the simulation is correct across all these different simulators, we expect that workload to run for like approximately same number of CPU cycles. And this is like pretty much what we see. And this runtime is, as I said, the time it takes for the simulator to for the simulation to finish. And you can see that it is like about 2.5x faster than the fastest available simulator. I think I forgot to explain what is random and stream. So those are basically the two workloads that we evaluate here. Random is basically a workload that performs random accesses to memory, and stream is accessing the memory in like a streaming manner, you know, like accessing consecutive addresses. Yeah, and so here we also have a metric request per second, which basically indicate like the throughput of the simulator, right? So how many requests are, well, how many thousand requests are serviced per second. And the last column is showing the memory consumption of the system that is running the simulator. And you can see that is also very low, which is a good thing. Okay. Here's a case study that uses, so here's a study that uses Ramulator to compare different DRAM standards. This case study was part of the original Ramulator paper. So like here using Ramulator, what we did was we compared how different DRAM standards will perform with different workloads. And we run the simulation across 22 workloads using a simple CPU model. And this plot over here is showing IPC, which stands for instructions per cycle. And this is a distribution, right? So across like the 22 workloads. So like here we show the minimum and maximum IPC of these 22 workloads, and also the average is shown with the blue line. Yeah, and like interesting observation here is that different memory standards perform like differently for different workloads. So there is not a single standard that is outperforming the others. So like depending on what kind of workloads you're simulating, one of the standard can be better than the others. but basically a single standard is not necessarily best for all workloads. So here's another more recent and more detailed study that uses Ramulator to analyze workload DRAM interactions. So I think this is also one of your readings. So you can find this link on the website, but you can also click the link here on this slide and read this paper. Okay, so I would also like to tell you a bit about the simulator architecture. So here, well, specifically the Ramulator architecture, right? Simulator architecture is a bit vague. So the design objective of Ramulator is to make it as extensible as possible, because like as we discussed, there are many DRAM standards, and even if we can develop a simulator to support all of them today, in the future, in near future, there will be other standards that we would like to also include to the simulator. So it is very important that the simulator is extensible. So the observation is that DRAM can be abstracted as a hierarchy of state machines. And this is like the key observation that this simulator is built on. Ramulator provides a standard agnostic state machine, which can be paired at any standard at the compile time. Okay, so let's look at the some of the classes that we implement in the source code. So there's a DRAM class, which is a template for building a hierarchy of state machines. Okay, so on the right-hand side, you can see a hierarchy of a DRAM subsystem. Right? So like at the highest level, we have a channel. So usually a single memory controller is interfacing with a single channel, but that doesn't have to be that way. A single memory controller can also interface multiple channels. And when we say a channel, this is basically a separate set of pins that are connected to the CPU, basically. So if you have two channels in the system, those are two memories that operate completely independent of each other, especially if you also have two memory controllers to interface with those two channels. If every channel is composed of multiple ranks, or it can also be a single rank, and every rank contains multiple banks. So you can think of rank as a, maybe like I will give you an example of a DRAM module, right? So like if you think of a DRAM module, you sometimes have DRAM chips on one side, on the front side of the DRAM module, and DRAM chips also on the back side of the DRAM module. So sometimes those chips operate as two different ranks. So basically different from channels, in two different ranks, chips are still independent from each other, but they share the same pins, right? So they share the same interface to connect to the CPU. And banks are basically different like groups of cells, let's say, that are like implemented inside every DRAM chip. So we will cover the DRAM hierarchy in more detail in the second meeting, where we will discuss works that use Ramulator in more detail. But basically, this was like, I hope, sufficient to explain you why we designed the DRAM class in this way as a template for like building like these different levels of the hierarchy as state machines. And this is what the source code looks like on the left-hand side. So here's the template, right? So like every instance of a level in this hierarchy, let's say, let's take the channel, instance of a channel as an example, right? So it has several or a vector of parents, and those parents are basically nothing for like the channel instance, because like it is the highest level of the hierarchy. But if the rank is the instance implemented using this DRAM class, it will have one parent. Excuse me, so this is not a vector, actually, this is a single parent. A rank will have a single parent. Okay, and every instance also has multiple channels. So this is a vector of other DRAM instances, and the children are basically other instances in this like hierarchy. So for example, a rank instance would have multiple bank instances depending on how many banks are in that rank. Okay, and we have some variables to indicate which level is this at and what is the index, right? So like what is the like rank ID here? Let's say if the memory subsystem consists of multiple ranks. Okay, so there are some states that we store in each of these instances, and these are node states to basically keep the state relevant to like operation of DRAM, or state relevant to the timings of DRAM. Okay, so let's see some examples here. So first we have a status which may change when the node receives one of the DDR3 commands. And so like, yeah, so basically this affects like which other commands can be issued after having this command issued. Okay, so like let me like provide you some like more additional information, right? So like a DDR3 commands are or the major DDR3 commands are activate, read, write, and precharge. So in order to access a DRAM row, you have to first activate that row. And basically only after the activate command, a DRAM chip or like a DRAM bank can receive a read or write command. So basically this is what the status indicates, right? So it is like indicating whether this DRAM bank has an activate issued, so it has like a row that is open, so it can perform a read write command. Or similarly, we can check the status to, or the memory controller can check the status to determine whether it can issue a precharge command to close an open row. If there is not an open row, it doesn't make sense to issue a precharge command, right? Okay, and there is also another state here, which is called next. Okay, so in this slide, it was like originally named Horizon, but it was then renamed to next. And this basically indicates the timing. So like the next cycle, the next like simulated cycle, where the next command will be correctly issued. So like the memory controller has to respect some specific timings between those DRAM commands, right? So like the next cycle after issuing an activate command, the memory controller may not be able to issue a read command because like activation takes some time, and the memory controller has to respect those timings. So after activate command, the memory controller waits for a certain number of cycles, and only then it can issue a read command. So basically using this next state, the simulator is controlling when the memory controller is allowed to issue a specific command after a previous command issued to the same bank or the same like instance, let's say, of the DRAM hierarchy. Okay, so there are also some functions that I would like to point out. So these are basically the functions that build the major part of the simulator, and like understanding those is basically understanding major part of like how the simulator operates. So there is a decode instruction or decode function that returns the prerequisite commands. For example, the activate command for a closed bank. So let's say there's a incoming request that wants to access, let's say, row 2. And if that row 2 is closed and there is no other row open in the same bank that request targets, then the memory controller will first need to activate that bank or activate row 2 specifically. And this decode function is basically for a given request and the address of that request that is going to be accessed, the decode function returns the next command that has to be issued in order to service that request. Another function is check, and this returns whether or not the timing is satisfied, right? So let's say the memory controller wants to issue a read command, right? But basically, it checks whether enough time elapsed since the last activate command using this function. If it returns 2, then yeah, it is okay to issue the read command. But otherwise, the memory controller needs to wait additional cycles prior to issuing the read, or it could be a write command as well. Okay, and I believe last function is update, and this basically updates the node state based on the issued command. So let's say we issue an activate command, it updates the status variable and also the next variables to indicate that, and to indicate the new state of the DRAM, both in terms of like the operation to indicate that a row has been opened, or also to indicate that when a subsequent read or write will be allowed. Okay, so here's how the decode function is implemented. So this is, I believe, not the entire code. It is like part of it, or maybe, yeah, I think this is the entire code here, but maybe changed a little bit. Okay, so let's go over this quickly. So the inputs are the command that the memory controller or the request is aiming to perform. So this could be either read or write. And wait, I'm confused. Okay, yeah, so this is the command to perform. So it is like either read or write at this point. And then this is the address to like read from, right? So this is an array of like integer values, and each value in this array will indicate the IDs in different levels of the hierarchy that I showed you previously, right? So from which channel you would like to read, from which rank, from which bank, and which row. So the first thing here that is checked is, so this is a lambda function, basically. This prereq is a two-dimensional array of lambda functions. No, it is. No, okay, sorry. Yeah, it is not a function. It is just a like a single command that will need to be performed before the command over here that is provided as a like argument to this function. And then this basically returns that command. So if okay, yeah, sorry, I guess the first thing I said was correct, right? So okay, so if here we first check if such a function, if such a lambda function exists, and if that is the case, that lambda function is executed using the basically pointer to the current DRAM instance. So let's say that this can be a bank, and that lambda function is like doing some magic to figure out what is the command that has to be performed in that instance, let's say a DRAM bank, before executing the provided command. Okay, and if such a command exists, if it is not equal to max, we basically return that as a like prerequisite, and otherwise we go to the next lower level. So let's say if you looked at the bank, next thing we will look at will be row, which is not actually implemented as a different state, but yeah, if we have like covered the rank here, next thing here to go will be to check the other level, right? So to yeah, to check the next level. Okay, and so here, this is a the prerequisite or the prereq functions for DDR3 here's one example of that. At a rank level, the refresh command requires a bank to be precharged. So how do I tell that? So just like basically for what this function is checking for is that whether there's any bank that is currently open. Right, so it goes like over all banks in that node, and then checks if there's an open bank. And if that's the case, then it returns the precharge command. So this pre-A stands for precharge all banks in a given rank. But if that's not the case, it simply returns the refresh command, which is like the same as the command that we would like to issue, right? So this basically means there is no any other command that has to be issued prior to this refresh. Okay, I hope that's clear. If not, please ask. Okay, so the next function is check, right? And here's its implementation. So this is basically, again, checking for whether the DRAM timings are satisfied. And here's how it does that, right? So for each command, Ramulator implements the next variable, and we in this function we simply check whether this next is not 0, is not -1, or it is smaller than the current clock cycle. This CLK indicates the current cycle that is being simulated. And if that's the case, yeah, it basically means the check failed at this level, and we need to look at some other levels. But if the timing is satisfied, meaning yeah, I mean, not entering this if basically means that this the timing is satisfied. Then the next thing what happens is if there are more children, this function goes and checks the timing of those children up to the like lowest level, which is a bank. And if all the timings are satisfied, then it basically returns like whatever is the check status for this current level of the hierarchy. Okay, yeah, we have animation. So like this part, as I said, verifies the whether the now is bigger than the next cycle at which the given command will be allowed to be issued to the DRAM bank or to this level of the DRAM hierarchy. So, and the update function is used for transitioning, right? So it's for transitioning between different states, for example, between a closed bank and a bank that has an open row. And it does two things. So it updates the state and it updates the timing. So it essentially updates the two variables that we mentioned, the status and the next variables. And it does that based on a lambda function that is defined in the DDR3.cpp, for example. So basically, yeah, so this part is the standard agnostic part. And this lambda function ties this to a specific DDR or specific DRAM standard, right? So here's the example, is the DDR3. And so here, basically, the DDR3 standard must tell how to update the status of this level. And this is how we achieve like basically easy extensibility of the simulator. And a similar thing is true for the timing. Okay, so this is not properly aligned, but this should be aligned to this timing part. Let me quickly fix it. Am I still screen sharing? I guess I'm not.
No, you're not.
Yeah. Okay, so this timing is the part that comes from the DDR3 standard and basically tells like what timing to respect. Right? So different timings may respect different timings. Some standard may make the memory controller wait for 5 cycles after an activate before issuing a read command, but some other standard may have that increase to, let's say, 10 cycles. Okay, so here's the source code to Ramulator and the original paper, which was published in 2015. So, okay, I was like wrong about the first day the tool was developed. Well, this is the day the simulator was like published in this journal called Computer Architecture Letters in 2015. But I would guess that the simulator was developed much earlier than this. And the source code is available on GitHub. So there are two versions of it. One version is like the just a plain Ramulator, and one version is Ramulator integrated to ZSIM. This is another full system simulator. And yeah, this version is better suited for studying processing in memory architectures and workloads. And yeah, so I will suggest that you look at both of these. Okay, so in conclusion, Ramulator provides out-of-the-box support for many DRAM standards. Some of them are listed here. It models the timing of non-volatile memories, and it supports multiple scheduling and row buffer policies. So you'll look at those more in the upcoming meetings. It is modular and extensible to different standards. It can be paired with other simulators, such as DRAM5 or ZSIM, as in the previous slide. It is written in C++ using the C++11 features. And yeah, it was about 2.5 times faster than the fastest open source simulator at the time the paper was written. And yeah, I guess we believe it is still the case, unless like there are new simulators that we didn't evaluate. Okay, so this was the end of the second part and also the end of the meeting. Yeah, so unless you have questions, so yeah, please ask if you have any questions. Okay, yeah. So then, thanks for attending the meeting. Oh, okay, before we finish, I think it will be good if we schedule the time for the next meeting. But maybe like we can end the lecture first, and I will stop the live sharing. And then we can see like what will work for everybody for the second meeting. Okay.